right, with 1 minute left, I'm going to introduce Astrid. Maybe you can introduce yourself in a bit, like what you do. I saw you have a background slide, but Astrid will today talk about geometric deep learning and surrogate models. You will not only talk about the curse of dimensionality and what that actually means, but we will also discuss the theoretical basics of geometry-based deep learning approaches and how to point out the differences to parameter-based approaches. So I know Astrid for a while. She's an expert in that field, so really looking forward to the talk. The stage is yours, Astrid.
Great. Okay. So yeah, thanks, Jousef, for having me, and yeah, so welcome to everyone. And yeah, I hope I can tell something interesting to you, and that you will enjoy the talk. So as Jousef pointed out, so I will yeah, talk a bit how deep learning can also revolutionize the world of engineering. And here, especially, we're given introduction to the method of geometric deep learning. And so I will also tell a bit about introduce just shortly the company where I'm working currently and where we are applying this technology. Then I will give an overview of the technology of the geodesic convolutional neural networks as such, and then also show just some, let's say, pretty pictures and some videos on so really that you can get a feeling where you can apply this to, and yeah, like what you can actually do with it, also in engineering day-to-day life. But before we get started, I just want to give a short overview of my background and why am I here today and why I might be the person telling you something about this. So let's start from left to right. And so I would say that my so to say love for engineering has started already some time ago during my first internship. And so then I decided to study mechanical engineering, and during the end of my studies, during which I had a scholarship at Lufthansa Technik. So pretty early in my career, I got in touch with airplanes and turbines and enjoyed that pretty much. And at the end of my studies, I got in touch with CFD, and I fell in love with it immediately. So since then, I stayed in CFD. So then I also did my PhD in CFD methods and put some coding capabilities on top of this. Then later I joined Siemens Energy, and there I was working in R&D in the field of aeroelastics, and there I gained some experience with design space exploration, optimization, and so to say also data science. And I think at that time, I already started to have the feeling that with the data we are actually generating and producing, especially with simulation, that there most probably is a lot more we can do with it. And already at that time, I got a bit frustrated from time to time, because I felt that, okay, when we do surrogate modeling during optimizations, we are not really taking full advantage of all the knowledge which is inherited in the data. So that was the reason why I decided to go a bit deeper into the data science direction. Then I joined Rolls-Royce and the R-Square Data Labs, working as an AI development engineer. And then, yeah, some time ago, I started my own business, really bridging the gap between CFD and data science and bringing these two disciplines closer to each other, and really working on projects which are at the interface of these, and basically just helping engineering engineers and yeah, small medium engineering companies to also yeah, hop on the train of data science and take advantage of all the methods which are available there and which are open source, and yeah, which you just kind of need to learn to apply. And now this year, I then joined Neuroconcept, and there I now work as a product manager. And yeah, so the product we are selling and building, and the software is actually based on geometric deep learning, and this is what I want to show to you today. So just a short slide about the company. So Neuroconcept is a startup, a spin-off from EPFL in Lausanne in Switzerland. So now we have a bit more than 30 people in the company. And the foundation of the startup is actually the work of the founder, which he did during his PhD. And yeah, so far we already have gained a lot of customers who were successfully already applying our technology. So yeah, we feel that what we do, we feel confident about what we do, and we really see a huge potential in this. And why this is so, we will now discuss. So coming to the technology. So I think that nowadays we find modern machine learning at all different areas. And I mean, not only like recommendation engines and yeah, I think when we already think already a bit about engineering, then it has already evolved from, like, let's say, classical regression modeling. So, I mean, of course, also machine learning, it's still regression modeling, but in some application areas, it has actually become quite complex. So here we just see a small subset of the application areas where it actually takes place. So protein folding, molecular discovery. Then we have all the whole area of natural language processing and computer vision. Oops. So when we now apply this to engineering data, what does this actually mean? So what can we do with this? So applied to engineering data. So when we see like the use case, what is displayed here? So where we can see under one on the left hand side, we can see the data set consisting of different shapes of propellers. And then the simulation results on this, like the pressure field on the surface of these propeller blades. So then this use case, if we would try to set this up with, let's say, more classical regression modeling, then the typical approach would be that the shape of these propellers is actually parametrized, so that you use a scalar representation of your geometry. So your geometry is described, let's say, per each blade is described by 10 parameters describing maybe the height, the width, for this propeller, maybe also the number of blades which appear on this. So with all of these parameters, you try to discretize your geometric space of possible propeller designs. So this is what you would do, yeah, usually with classic regression modeling in engineering. And then you can take these different parameters which do describe the shape, and then this you feed into your regression model. So state of the art in engineering is, for example, Gaussian processes, so kriging. But yeah, you can also do like any kind of response surface modeling. And then usually what you try to achieve with this, and what you try to predict for a new set of parameters describing a new geometric shape, is then again a scalar output, so an integral value, what you are really interested in. So for example, here it could be some kind of efficiency or the resistance, something like this. So let's say a really to you important KPI of your engineering problem. And so the difference to the case what we can see here and the model what we are using is really, on the one hand side, we are not only able to predict scalar integral values like efficiency or resistance, something like this, but we are also able to predict the full spatial resolved fields. So this is what you can see under the number 3 on the right hand side, so that you can really predict, for example, the fields on the surface of the blade, but also in the 3-dimensional space around it. So that's one thing what really is important. But the other thing, and this is already really going to the roots of the capabilities of the geometric deep learning, is you do not rely on this parametric representation of the shapes, but you are presenting the shape directly as it is to the model itself, and the model itself then extracts the important information from the shape itself. And so as I said, the geodesic convolutional neural networks, which are used for exactly this, like extracting the important information about the shape itself, which is actually present in the shape as such. So we don't want to use the parametric representation, but we want to use the shape itself. So this geodesic convolutional neural network is a subclass of graph neural networks. And so this is something what I like to compare to image recognition, because I think there are definitely some similarities, and I think it makes it can make it easier to understand the technology behind this. So I feel it is quite similar to image recognition, but then in 3D, and of course it's only partially correct. But if you, I'm sure you have heard about image recognition. So you present your model also already during training with images, with pictures, and then one requirement is actually that all of these pictures have the same size, so they do have the same amount of pixels in X and Y, so in these 2 dimensions. And then when we think about the distribution of the pixels, then it is already quite obvious that there we are in a regular Euclidean space. So the orientation of these pixels and how, like the pattern of these pixels, it's always the same. So this is something what then can be taken advantage of. So we do have these patch operators, so to say. This is also what we can kind of see here on the right hand side. And these patch operators now like move through these pictures and perform convolutions or other operations on the values of these pixels. And so, yeah, as I said, for performing these operations, it is taking advantage of this regular alignment of these pixels, and that you are in this really regular space. So you can trust that the pixels are always there, and then you can perform these kind of operations with it. Yeah, so but this already also shows like the limitations which come with this. So when we now go to let's say the irregular space. So and now here in this picture, which I actually, so this is just a short clip from a video I actually just got from YouTube. The link you can find down there. And there it is also really good explained a bit more in detail what graph neural networks are. So this is already going to the irregular space. So if we again now think, now we have these dots, and instead that these are our pixels from the example before and the picture. So now these dots represent vertices. And these vertices, they hold values or let's say characteristics. And so now I can also go through this kind of space of vertices, and then I can also move from one vertex to the other and perform also operations on this. So, and these operations can then also be convolutions or other operations like building the average, and then assigning these new values to these points in my graph network actually. So also here it's really about extracting like a patch from this local system of coordinates, and then we apply some function to this. And what is really important to point out here is like the idea of this graph neural networks is actually to really take advantage of this information which is within the graph when it comes to the relation between the vertices. So there is some information inside when we think about which vertices are connected and which vertices are not connected. So this inherits some additional information we also want to extract from this kind of from this kind of graph. And then it's like really so why are we now looking at the graph neural networks when we think about engineering problems? And this is just something what I want to show with this picture. So that's just showing the shape of a drone. And these three pictures actually just show different representations of this drone shape. So the first one on the very left is some kind of voxelized representation of this shape. Then in the middle we have just a point cloud, and then on the right hand side we do have a mesh. Yeah, just a surface mesh representing the shape. And so we do have, yeah, as we can see, we do have different ways of presenting these shapes, and the representation actually needs to fit the application. So when it is, for example, about shape recognition, so let's say we just want to have a model which is able to do some classification, whether it's a car or a plane. Then the voxelization and this this voxelized representation might already be enough and sufficient, because for just the pure classification and doing a comparison and making a decision whether it's a car or a plane, this is sufficient. So this might be enough. But if we now think about fluid dynamics, so where really small changes in the geometry can have a huge global impact on the overall flow behavior around the structure, so then we really want to be able to capture these impacts. And yeah, like small tiny changes to the geometry, we won't be able to capture these with a voxelized representation of the shape, as you can already imagine just by looking at this. And the same is actually also true for the point clouds. So for example, if we look at the wing structure there, then a point on the upper part of the wing can be really close to a point on the lower part of the wing. But when we look at the mesh, so when we really look at the manifold of the surface, then these points are actually really far away from each other. So this is the reason why the mesh presentation with the edges between the vertices and the additional information about which vertices are connected to each other is actually holding some really important additional information, because yeah, as I said, I think with a thin wing, this is just something what is good to imagine that yeah, their 2 points can be really close to each other, nearly as close as if they were on the same surface, but actually they are not. So if we look at the surface, then they can be really far away from each other. So now when we now think of our shapes and our geometries and engineering in these manifold surface mesh representation, then we can already think about these as having a quasi two-dimensional graph representation in this manifold space. So we could think that now the mesh of the drone, what you can see on the right-hand side, we can, like in our head, imagine how we could unfold it, and then we would have like a 2D graph, which would actually look pretty much like the graph what we have seen in the video. So now on this quasi two-dimensional manifold representation. Now there again we can again define these kind of patch operators we have already seen in the image recognition. So now for these, let's say the challenge compared to image recognition for these patch operators now is that these vertices, they are not in the regular Euclidean space. So we have to define additional local coordinates, which do actually then represent the neighborhood of our center vertex, which we are currently looking at, and its neighbors. And so then also again, these local coordinates, which are representative for the neighbor, for the relationship between the center and the neighboring vertices, this is already holding a lot of information. Because when you think about the meshes and you have a part of the geometry where you have like really a lot of small details and features inside the geometry, then this would actually mean that there you have a lot of vertices close to each other, while on other parts where you have just like a straight surface, so there the surface is represented quite good already with some vertices which are quite stretched out along the surface. So here, what's like pictures and pictured in on the right hand side, these kind of local coordinates for representing the relationship between a center vertex and its adjacent neighbors is defined by the radius between the center and the adjacent vertices and the angle. And yeah, so with these local coordinates, then again we can define this patch operator, which can then also go from vertex to vertex and calculate some convolutions or also other calculations similar to the image recognition, and by that calculate specific features which do represent this geometry. And yeah, so in the end, this actually leads to a translation of this two-dimensional surface mesh into a space where we have the number of vertices times the length of the feature vector, what we have just calculated. And so you have created, yeah, just like a number and a matrix of numbers representing your shape. So then for when we now look at the overall software and the product what we are using, and as I said in the beginning, we are also able to predict spatial resolved fields. So then we can see already that that actually the shape is only one part of the model, and the other portion is then of course the field data, which also has to go into the model. And so here I've just linked also the paper, which is like the essence of the PhD thesis of our founder. So if you're interested, then there you can also read a bit about this. So, but now before I show some applications and some use cases, I actually also want to give some.
Just real quick, Astrid, if you go to the previous slide, just one, and what was the problem statement here? Just if you look at the slide from a like a layman perspective, what was the problem statement? To explore the design space, or what's the problem?
Oh yeah. Oh yeah. I'm sorry. So the problem statement here, of course, is that if you want to run a simulation and you want to get the simulation result for a specific shape, then it takes a really long time. Usually, I mean, it does depend on the fidelity of your simulation setup, but usually it takes a really long time. So then if you have trained such a model to be able to predict these quantities of interest, then this can be done in seconds. Thanks for pointing this out.
Astrid, I would have one additional question about the mesh sensitivity. Are you making sure that every simulation that you are training the AI with is like converged accurately, or like there's no a mesh independent study has been done accurately?
No, I mean, of course, we cannot do this because we do rely on the data of the customer, so we do not have control over the data generation as such. But what we can do is actually so the model itself during training time is able to pick up what we call data uncertainty. So just by taking in the training data and then finding out if there are some bits in the data which are actually not learnable, so which could result from let's say not fully converged simulations, because if you think of not fully converged simulations and where your result is actually still like a bit fluctuating around an average value, then your extracted solution does actually depend on the time where you cut off your simulation and you extracted your results, right? And then like this spread or fluctuation around the average value. So this is actually something the model cannot pick up. Why? Yeah. How should it? Because it's not trainable. There's not a logical relationship. So this is something what is then recognized as data uncertainty. And this is then actually also something what is predicted alongside with the fields or other quantities of interest. So then there again, also for every prediction, you would get a distribution actually. So your field would then be average value, and then you would also see a distribution of these values, and yeah, a range of uncertainty.
Basically, that brings us back to Gaussian processes again, right? That you talked about. Yeah. Okay, cool. Thanks.
As just I promise one last simple question for me. Is there, if the left side is called, is the right side called a simulation or not? Just out of curiosity, in technical terms.
Excuse me. There was the audio. Yeah.
If the left side of your image is called a simulation, is the right side called a simulation or a prediction?
No, the right side is the prediction. So on the left hand side, so what we can see under one, this is actually all the data which goes into the model during training time. So there we do have the shapes and we do have the fields and all the results coming from the simulations. So everything we have, we feed into the model and we train it. And then if the model is trained, then it just needs to be presented a new CAD geometry and then is able to predict the fields.
Okay, got it. It's okay, 1, 2, 3. Got it. Thanks.
Great. Yeah. And actually, thanks for asking these questions. I feel I ran over it. Yeah. Okay, but my passion is in CFD, so I'm definitely an advocate for simulation, and I just want to make clear or point out that although we are now able to come up with these really cool and fast neural networks, so still, simulation will not become superfluous, and we do rely on high quality data here as well. So yeah, really getting high fidelity simulation result is something what is essential for getting good models. Yeah, as we just now pointed out in the previous discussion about the data uncertainty. Yeah, because if the data we train on our model is shitty, then we cannot expect the model to get great results. And this is just something what I want to highlight here, because yeah, let's say in the beginning we were just relying on experiments, and even there the accuracy what we can achieve and how close we can really get to reality relies on the setup. So which excerpt of the overall reality do we actually look into? Then we always do some assumptions for setting this up. So this is the reason why also for experiments the accuracy can already vary a lot. Then we got the simulation. There we can introduce errors on multiple levels. I mean, yeah, I make some simplifying assumptions, then I do make some modeling errors, then I put some discretization on top of this, and all of these are levels where I can introduce additional errors. And then, yeah, I mean, the experimental data is used to validate the simulation to maybe then, become better in the modeling approaches or whatsoever. And so now we do have the machine learning models, and yeah, I mean, it is a kind of regression, so it does rely on the training data. So yeah, it cannot be better than each one of this. So maybe it can, in some cases, which can actually even out some fluctuations, for example, but in general, it cannot become better than the data what we put inside. But what is also pretty nice about this is that the machine learning models can actually become better than simulation, because we can train them also on experimental results. And this is something what is also quite nice, because then we can actually gain a higher accuracy than with simulation. But yeah, so basically to conclude on this, I just want to say, so we do still rely on simulation data, and so it is important that we develop our capabilities there even further. So yeah, why is this now a huge thing when we think about this geometric deep learning? And what are now the advantages compared to the more classical or traditional approaches? So the time when we just go through the table from top to the bottom. So the time, what is needed to create these predictions, that's the same. Then we can also use both of these models in the context of optimization. But then here it starts already that on the left-hand side with this traditional parameter-based approaches. So there, the possible design space is really limited to these parameters. And I mean, I've spent actually a lot of time in my career doing these kind of response surface modeling and then performing optimization on them. And one reason why then the data and the models cannot be used any further is that if you gain more knowledge about your problem and you're actually able also to maybe create more complex designs, then you cannot use these response surfaces anymore as soon as something in your parameterization changes, because yeah, then the model is just useless. And I think this is actually something what is really great about the geometric deep learning approach, that here you're really completely free, so you are not bound to any kind of parameterization. The model is trained and is able to predict really just based on the shape. And yeah, so this actually also shows that this is something a great potential for the model, because it can be continued to train always further. So from one design program to the next. So the data which is actually presented to the data, it can be improved over the time. And this actually then also allows the topic of transfer learning. So really taking results from one design program and transfer it to the next design program. Yeah, because as I just mentioned, so usually the more traditional approach, what I have also experienced is that for every design project you build your specialized surrogate, which is based on the currently used parameterization, but most probably you cannot apply it to the next design program. And that's something was really nice, because here now you have the possibility on the right hand side to really train and build a more general surrogate model, which is maybe or hopefully able to cover all of your design projects. And even if it is not in the beginning, then you are actually able to increase the data set and to add additional data points to your training data and improve the model while you go. And yeah, so also, as I said, another thing what is nice here is that you're also able to do data fusion, so you can combine data which comes from simulation with other so yeah, like really heterogeneous data sources. So you can combine simulation data with experimental results and really combine these data sets and train a model on both of them. Then you can also apply weights to them. So for example, if we think about CFD again and training a model which would be able to make the predictions, so that you don't need to run the CFD simulations for your next design program, then you can actually also train it on a RAND simulation, but also on higher fidelity LES simulations. You can then weigh the LES simulations, give them a higher weight, so telling the model right away, okay, actually this is more trustworthy data. And yeah, I think that's then why do we want to use these surrogate models or response surface? So yeah, of course, the one thing is it is really nice to be much faster than with the simulation. So every time you come up with a new shape, and or with a new design, and you are able to get the field predictions in seconds rather than running a simulation, which takes a lot of time. So that for sure is nice. But I feel like the full value comes when it is about running optimization, and that then actually the evaluation of new shapes, of new geometries, which can happen or which will happen up to multiple thousand times until a really optimized shape is found. If this can be done in seconds, because then, then the speed up really brings its full potential in.
Astrid, you're way too smart for me, so I can't keep up. But I will tell you, to be honest, thank you so much for opening up my brain. Yesterday we took a course on physics-informed pins, neural networks. Just curious, what's because here it sounds like you're informing as well your neural network through these the data training sets. I'm assuming it's different, but somehow related or not?
No, it's actually not related at all, because here we do so what we input in the models here are just the shapes, but then for predicting the fields, we can actually also apply the same technologies as physics informed neural networks. So yeah, I mean, just to give an example. So for example, in this loop, what we see here, so we do have our trained model, and now we produce a new generated shape, which one of our designers came up, and we hand this over to the model. And then we get the prediction for our field, and maybe not only on the blade surface, but really in the overall simulation field, so in 3 dimensions. And we actually also have like an inlet and outlet. So then if we have the prediction of the field on this, then we can actually do some forward calculation of the Navier-Stokes equation and really make sure that we do have reached mass conservation, for example. And if we have not gained this, then yeah, we would give some penalty back to the model. But yeah, but this has nothing to do with the shape.
Okay.
So
yeah, the reason I thought it was, remember now, we adjust the CNN's loss function with some sort of understanding of the physics, and I remember that part. It's because the training data was reproduced using, I guess, on the left, what appeared to be like some sort of numerical method. I was saying, okay, but yeah, it's just training data. That's fine. I get it. Thank you.
Yeah. Okay. So so usually what we do for optimization, so we start with some evolutionary optimization. So there, then the optimizer would just like put points in the overall design space, and then generate new generations from the best samples. That's really something for global optimization. And then when we at the end really have reached already an area where we think, okay, we are confident that we found the global optimum, then we can actually also apply a gradient descent, because just like the models what we use here, so they are fully differentiable, so that we can actually apply a gradient descent optimization algorithm here. Yeah, then again, I cannot say this too often, it's non-parametric, so that's just really nice. But yeah, so if we now use this model actually within the environment of a traditional design, design concept in the engineering company. So then, I mean, usually if you do this, then your designers, they still do rely, especially for optimization, they do still rely on parameters. And then even if you have the freedom in theory that you can present any shape as you like to your model, then within the greater framework of an optimization, you would still then fall back to a parameterized representation, because the optimizer itself is just able to to adapt parameters, and by that then get the feedback whether it went to the right direction in the design space, or if the parameters have to be changed again to get closer to the optimal design. So this just means that, yeah, even though then you might be able to change the parameterization from one optimization to the other, you then are still like a bit bound by the classical parametrical representation of your shapes. And this usually also holds another challenge, because what you really want to avoid when doing parameterized geometry representation in the course of optimization is that you are able to like reach to the same shape with different set of parameters, because this is like the worst thing what can happen, because then the optimizer is completely confused and does not know what to do. So this this can actually be a challenge, because you really have to make sure that your parameterization of the geometry is like unique, and that you can just get one shape with one unique set of parameters. And this is something what's also sometimes pretty hard to reach. And so here then you can we can actually also make use of something else. So we also came up with our own generative model. So that's a kind of implicit shape representation based on signed distance functions. And this then again is really it's a smoother representation of a shape. So if you have trained a deep SDF model from the shapes which you have created up front with your parametric design, then you are actually able to create shapes smoothly within this overall presented design space. And if you do something like this, and this does not have to be this generative model here, so it could be any kind of generative design, but I just want to point out this geometric deep learning approach for the predictive model. So really being able, by just processing a new shape coming in a native CAD format. So the real potential of this can just be really taken into account when you put something up front, which is also not parameter based. And if we now really think about this overall optimization loop, so then we can see, okay, now in this example, we are really like parameter free, because we use some kind of generative design, which comes up with new innovative shapes. And these shapes can then directly be taken in whatever native format they come, as in STEP or STL file, and can be presented to the deep neural network, which then is able to just process this shape and make then predictions in the field, on the surface, or whatsoever. And then the optimizer can work its way around to a really optimized design. Okay, and so with this, I just want to show some use cases and where this has been applied already. So yeah, maybe just again what we were discussing also earlier, like really what is the problem statement, or what is now the huge advantage of this is like usually the standard design workflow, yeah, it's like you have a designer, you get a design, then you have to do some preparation of it, then you can run a simulation. I mean, of course, you can also have this in parallel, but the time you need for getting the results from a simulation, this is just, yeah, even you can parallelize as much as you want, but there's still some time you have to wait. And then afterwards, then you can come up with your next design revision. And so, yeah, it just takes some time. And so if you then really get rid of this waiting time for the simulation, and you can actually take advantage of a model which was trained on some legacy data from previous design projects, then you can just speed up the overall product development process by a lot. So this is just something I want to show, like just to, yeah, put some pictures to this, how this can really look like when you actually make prediction of fields. So it's not because it's not limited to CFD. It's basically, I mean, every data can be processed. So everything what you can simulate, you can also train a model on. So here it's more structure analysis example, and yeah. So as you can see, it's yeah, it's just one example which just shows really nice how this field prediction also for finite element problem can look like. So then this was just one example, one use case we had together with ESA. And so here was about some thermal behavior, and like here the specific thing I just want to point out is that this is something which is directly accessible from within the CAD software. So within the CAD software, the designer is able to create a new design, and then from within the CAD software via an API, the predictive model can be called, and then the designer can see directly the results of this design change. And yeah, I think this is just something what is really nice, that you have this instantaneous response to your design changes. And yeah, if this is then also accessible from within the CAD software, yeah, I think this is just really also just to put some buzzwords, but really democratizing the simulation and make it accessible also to the designers really early in the product development process. So then this is one example from Airbus. So here it's really about the pressure around the wing surface, and yeah, just showing how much faster you can be yeah, when you use such a model instead of running the CFD simulation. And then that's another example just for some conjugate heat transfer problem. So here it's also that the design as such is like really complex. You have different topologies, so you would just not be able to combine this really in one parametric CAD representation. So you would, yeah, so this would already be really hard to have to describe different topologies also in the same and to cover this in the same optimization loop. So yeah, this is also something was really nice because it's parameter free, and by that it's also not bound to specific topologies. And yeah, So with this, I'm already at the end, and so I hope you enjoyed it, and I'm open for questions, for more questions if there are any.
Thanks a lot, Astrid. Great talk. Any questions, guys, to Astrid? I'm not sure, maybe I can ask a question, which is on the validation of the results. Yes. How do you actually validate the results? I think you have mentioned it briefly, but can you maybe emphasize on the validation aspect?
Yeah, and actually, I have not mentioned, I have not mentioned it at all. But yeah, I mean, the validation for this is actually done as an every machine learning. So in the beginning, you split your training data set into a train and test data set, and then yeah, this data set for validation is not touched unless for validation purposes.
So basically, you only use the data that you're using to train the AI model on.
Yes.
For validation. Okay. When it comes to physical validation, for example, if the AI comes up with a weird shape, which might not make any sense, that probably takes the ingenuity of an engineer to say, okay, maybe that doesn't make sense. Does that happen sometimes?
Yes, yes, of course. But I think this, so I have not seen that like really some weird shapes were generated. But I mean, in general, and this is something what is actually, I think, true for every surrogate modeling and every optimization project. In the end, the design with what the optimizer comes up and says, oh, I think I found the optimal design. Of course, you will always take it and run the simulation again to really make sure that the results are actually true. And I mean, most of the times it will not be a perfect match, but yeah, hopefully you have gained something. At least, but yeah, I mean the surrogate model is never 100% correct, so you always have to rerun your best design in the end and validate it by yourself.
Yeah, if we talk about ROI, maybe you can pick a specific use case. What are we talking about in terms of time savings and maybe investment savings if we use data-driven approach versus a classical traditional physics-based approach of simulation CAE tools?
I think actually that these are numbers you can, I mean, basically, to be honest, you can generate any saving what you want, because if you think of let's say a more low fidelity simulation, or just not a very complex simulation, the grid is not as large, then maybe your gain is just going down from 1 hour simulation to 1 second prediction. But you can also have like really complex workflows, and then you can even think about some interdisciplinary things. So where you then also can combine a surrogate model for the fluid dynamic side and combine it with a surrogate model for the structure side. And then usually these things of interdisciplinary stuff, for example, from area elasticity, where I come from, there you would have like optimization projects which run for 6 weeks, and then you are able to bring them down to 6 hours. So
nice.
Yeah.
Very cool. I was wondering, Astrid, about the physics and what Walid asked that I think during the talk, which is, how do you make sure the physics is accurately captured? I mean, it learns from the results, right? But the thing is, what I always have in mind is that the simulation itself is a model. So basically, we're building a model from a model. Yes. So how do you actually make sure in the back end, or like maybe the architecture knows the physics somehow? How do you make?
No, it does not. It does not. And I mean, yeah, that's the thing. What I wanted to point out with this one slide, that we do rely on high fidelity data, and we cannot become better than the data itself. And it is actually in our responsibility to validate the outcome of this. And yeah, so there's no check inside the model to make sure that the physics are actually fulfilled. No.
Got it. Okay, cool. We have one question in chat, which I think talks about transfer learning. If my data set is of a car simulation, and in the next step I import a CAD geometry of a bike, will it be able to predict that?
No, that's
It's a bit too much.
That's a bit too much. So when I talk about transfer learning, and let's say I have trained a model on different car designs for different designs of the rear body, and then maybe having what is it called, this thing what you can put on top.
Spoiler?
Yeah, thanks.
Spoiler,
So maybe different spoiler designs, stuff like this. Then you can actually use the transfer learning to take the same model and then apply it to the next design project, for example, for changing some parts in the front of the car. So then it will not right away reach a very high accuracy. So then you might need some additional data points from your first different geometry changes, rerun some simulations on this, retrain the model with it, but then you will be able to reach a high accuracy, like really fast and much faster compared to training a new surrogate model from scratch. Yeah, and this is actually also something what the model itself will tell you, because alongside with the prediction, it will also give you a confidence index, a confidence interval, just like saying, okay, so from the overall design space, which I have seen during training, this presented geometry is like really far off. So do not trust my prediction, better run a simulation and feed this additional data point and retrain me with it. Or if the new presented geometry actually lies pretty well within the envelope of the training geometries, then it will say, oh yeah, I'm super confident that my prediction is right because I have seen other samples which are in the same area of the design space.
Got it, makes sense. How does it facilitate actually work for engineers? Are we speaking about simulation engineers or CAD engineers or both?
So we are actually so we speak about both. So like the really envisioned user or the envisioned end user for the software is actually the designer itself. So who is then really able to already see the implications of his designs right away, and then also already get a feeling of, okay, so this change is going into the right direction. But the setup of this totally relies on one expert who owns also the simulation data with which the model is trained.
Got it. Okay. Astrid, thank you so much. We have 1 minute left. Any last words from your side, or maybe recommendations if people want to jump on the AI hype train? Let's call it like that.
Yeah, so of course, maybe if you want to jump on the train and you are still looking for an open position, then also check our homepage, because yeah, we are always looking for talented people, and yeah.
Great. All right, Astrid, thank you so much. You will have 2 more talks in the cohort, guys. So Astrid will also code up a CFD Insights app, or like how we can post-process CFD results, but you will also talk a little bit about women in STEM. With that, Astrid, thank you so much. The next session in 15 minutes is an introduction to reinforcement learning from my friend Alessandro. With that, I'm closing the session. Astrid, thank you so much, and hope to see you soon.
Thanks a lot for having me. Have a nice evening.
Thanks.